Right, speech and sound. Today we are gonna be looking at the audio analysis pipeline. So basically, we are gonna try to look a little bit on every step of the process of someone's process when they want to analyze audio for research purposes, right? We're gonna look at sources. Going to look at how we extract audio from different sources, how we pre-process audio, how we extract some basic features that are very, very helpful. We're going to talk a bit about transcription and speaker diarization, something that is extremely useful. We are going to speak generally, mostly in the introduction, but throughout, I'm happy to bring this element in more and more, about generally the social science aspects of analyzing audio and what kind of research questions we can answer potentially. And then also we're gonna speak a little bit about general validation when it comes to this kind of data. So there is both importance in working with sound, but also an opportunity. So basically, we've seen a lot of text analysis in these courses, and we know that when it comes to text analysis, those studies look at what actors say. But when we are dealing with audio, we can see, you can also study how, when, with whom, under which conditions they said what they said. So we are going a little bit deeper than the actual thing that was said to how it was said. So obviously we are aware of transcription and getting the data out of an audio file and working with a transcript. We're gonna look at that a lot. So a lot of research is being done with transcripts of audio files. So the text element of a file, but a lot of information is being lost when you're doing this transformation, when you're extracting transcripts. So social scientists are increasingly studying how speech is delivered, not only what is said, so not only the content of the speech, but also the way it was delivered, in the conditions it was delivered, etc. So some of the things that people look at is vocal pitch or intensity. So it's been used to measure emotional engagement in legislative speech, for example. So I have references for all these studies at the end of the slides, and you're welcome to see them. So a study from the US House of Representatives looked at how Congresswomen spoke more intensely when they were discussing women's issues. So, and you're going to see that some of these, I mean, the majority of these examples are from the political science, which is where I come from. And I hope this is relevant for everyone. In my eyes, it is relevant for everyone, but it is a little bit focused on political science and a lot on speech making in parliament. So another study in the German Bundestag, very recent study showed that MPs show increasing engagement when they speak about climate issues, and they use the speech tone and the interaction with other speakers to see if there are latent meanings like skepticism, something you cannot capture simply by looking at the text. And then another study looked at Supreme Court oral arguments of the justices in the United States, and they showed that the vocal tone revealed if there was skepticism that the transcript would miss, and that's what they show. Different kinds of research questions become possible when we look at audio. So again, in this realm of political science and representation, you can look at who speaks with emotional investment on which issues, right? Which politicians. Do politicians speak more emphatically when voters agree with them? So questions like that. So a study in the US analyzed video and audio to try to understand emphasis and link it to constituency opinion. So do my voters care about this issue? So I'm going to emphasize it more. Beyond, so if we were to do a regular NLP study, natural language processing text study, we would look at all the questions or all the speeches that an MP did, right? And we would count how many of those questions or speeches were about that topic and in what way were they phrased. But then when we look at their speeches and how they interact to answers, questions, you can maybe see if they put more emphasis on certain topic, if they speak more passionately about a topic. And this study has connected it to constituency opinion. Very interesting in my eyes. We can look at things like party competitions. So how do audiences inside the parliament react? So this is really, really interesting study in the Bundestag, the German parliament, where they measured applause patterns. So how many times MPs clap and how strongly they clap, within party clapping, towards the opposition. Very, very interesting stuff. But also there is a sort of wave of relatively new studies where they bring some methodological caution to these. And we're going to be talking a little bit about this because, I mean, these audio features like pitch, energy, applause, all of these need validation. So they are proxies of what we're trying to measure. They're not direct measures of emotion, right? And they are sort of raising caution around the issue of how easily these are being used. However, there's a lot of validity if you do it right, and we're gonna be talking about that. So just very briefly about this emphasis study, which I feel like it was very interesting. So the idea is that they took speeches and they both looked at video and audio at the same time. And they did some neural network analysis. Let's not focus on this middle part here. Let's focus on the fact that they used both the audio, so both what the way something was said, but also the physical body elements of the MP delivering the speech. And they ended up having a scale from -3 to 3 of what they call speech emphasis. And they did this with 77 hours of debates video. Over 2,000 total speeches from over 500 legislators, and they managed to measure this and validate their measure. Pretty interesting still. So the idea is that they would have this emphasis score again from -3 to 3, and all the speeches are falling somewhere in between. But then there's this blue line of low emphasis, which is the speech by this person here, John Conyers. And then a speech with high emphasis, Rosa de Lauro. Over here, you can see the movements of the hands, a lot of movement, and also the audio features that are there. So I also aggregated sort of the kind of questions we can ask into 4 families. Like we can speak about agenda and content. So what issues do people emphasize in social media videos, for example? We can look at style and emotion. When do people sound emotionally intense when they're talking about what topic? For example, interaction and power. Who gets to speak? Who interrupts and who is interrupted and by whom, right? So also very important. There are a lot of studies of parliamentary debates. Again, sorry for bringing this up all the time, but it's just where I'm more familiar with the literature. Where researchers have looked at how women are predominantly interrupted much more than men in parliament. And they measure that by doing audio analysis, because if you look at the transcripts only, you cannot really see interruptions if they are very subtle. They are not registered. You can only see if someone else takes the floor. In most cases, in some parliaments, they do measure interruptions. They do have interruptions in the transcripts, but in the majority not. So this is like one more thing you can do extra with this. Yeah, and we can also see a platform and communication strategy, obviously. I mean, how do people communicate differently, different arenas? Is it more like, is the audio intensity different when you speak in social media versus when you make a video or in parliament or a video about your campaign or something like that? And other potential metrics when we use audio files, we're going to look at some of this. We're not going to look at this, but these are additional. So we can see total speaking time, we can see turn length, interruptions, response latency. So if someone takes a moment before they respond, maybe they are trying to gather their thoughts, but maybe they're not ready. Maybe they are being pressured by the interview. Speaker entropy, if their participation is balanced, and etc. So let's speak a little bit about sources, potential sources of audio data. Is there any question at this point for the sort of research question part? What kind of questions we can formulate? All right. So where can we get data from? So to do audio analysis, right? I mean, obviously, data from political institutions, as we mentioned a couple of times already, parliamentary debates, committee hearings, court arguments, council meetings, public consultations. In many, many countries and cases, these are being recorded, and you can go and get the video data or export only the audio data. I'll just give you an example from the European Parliament. The European Parliament has a really, really cool page to access speeches from all the sessions and all the bodies. So, for example, if we look at the plenary session, and you can search by a name, I'm going to look at a Greek member of Parliament, Georgios Aftias, from the European People's Party. And if you look at them, you're going to see their latest speeches and the sessions that they participated in. And you click on that, you get a video that you can also download. So yeah, potentially I've linked to the wrong page. Yeah, no, you can download here, as you can see. But there's even another tool that I'm now missing. Let me. Yeah, so this is just the link. I'm gonna figure it out and paste the link. But this is, for example, just the snippet of that particular session that this particular MP from Ireland gave a speech about something. So this is just a couple of seconds long, and you can download this particular video only, and then extract the audio and do your analysis. And you have this for every MP. There is an API as well that you can access and have this data drawn more automatically. Not every parliament is like this. And we are going to use actually this video of hers for our analysis later on. Obviously, not all parliaments are as good as this and are as organized as this. If I may say, the Greek parliament, for example, is completely on the other side. Very, very low quality of data. You need very special permission to get access to some of the debates, and you got to do a lot of work. But in other parliaments, the work is done for you by some IT team already there. So it's something to think about. So let's continue. Online platforms, obviously, YouTube videos, podcasts, live streams, social media data from TikTok and Instagram. Many people use these and they analyze the video, but they also analyze the audio, right? And I mean, the majority of workflows just take the audio and transcribe it, and they focus on the text. Today, we're going to be looking at what you can do with the actual audio. But these are sources of that. News and broadcast media, like TV debates, radio interviews, press conferences, talk shows, a lot of data out there that could be potentially used. Many TV channels and stations and radio stations publish their shows. They keep record of the shows, and they allow it to be publicly accessible. Obviously, research-generated data, when we hold interviews with people, when we do focus groups, when we do ethnographic recordings, etc., we have a bunch of potential audio data to work with. Then there are these public event recordings that happen sometimes. So, for example, we are doing a lecture today over Zoom, but Sumaya has decided to record this, right? Obviously, and actually Zoom automatically transcribes this as well, if I'm not mistaken. And she gets a nice transcript. She can then put on AI and make a nice summary of what was said, etc. But imagine any kind of event like a protest, a campaign rally, town hall meeting, NGO event. So all of these things could be recorded by some camera or some microphones in the area, and this is phenomenal data. Like for someone, let's say, that is studying protest, they can do a lot of things about the intensity of the protest, the gauge the crowd's participation and involvement, etc. Many cool things that can be done. Yeah, and then there are these sources that are text linked. So we have the audio, and they are assigned to official transcripts, subtitles, and captions when we have in videos, Hansard of the parliaments, etc. Sometimes it's also very useful to think that beyond of just grabbing that the .wav or .mp3 or whatever kind of audio file you're getting, it's important to keep in mind that metadata can be very useful. So who's the speaker, who's doing that audio clip, if they belong to a party or have some specific role, obviously date, a venue, platform, topic, transcript, availability, like audio quality, very key, and we're going to speak about that, and also permissions, right? So think about beyond just getting the actual unit, which is the audio snippet. Think about what metadata you could be collecting, because those can be really useful in making some preliminary analysis. Before I continue, there is a question from Omar Kasim. When evaluating the style and emotion of a speech, are the metrics typically absolute, or are they relative to the context? For instance, what sounds like a neutral baseline tone in one language or genre might register as highly emotional or unusually flat in another? That's an excellent point. We are going to talk about this a little bit more, but it's pretty key now that it's being mentioned. So there are many things that can hinder the validity of our measurement. I'm going to take you a step before language, and imagine we care about the amplitude, the intensity, how loud a voice is, how loud an audio file is. We can measure that by looking at the decibels, and we're going to do that. We're going to capture that exact thing in Python later on. But imagine, I don't know if you can see me, but I imagine I have a microphone here and I speak here. The moment I bring the microphone back, I'm still speaking with the same tone, but you're listening to me as if I'm speaking, as if I've lowered my decibels. If I bring the microphone close, then again, I'm speaking with the same exact tone and level, but it feels like now it sounds like I'm speaking much louder, so the decibels go up. So even the measurement instrument matters a lot. So where the microphone is it consistent for all members that are participating? So exactly when we're doing comparative work, we need to be sure that we need to do our best, actually, because we can never be sure 100%, but we need to do our best to hold all other variables constant and stable across all our measurements. And language or gender, as you say, they could carry their own, definitely language, it could carry its own modifying characteristics in terms of all the things that we're going to measure. But let's continue, and we're going to tap on this a little bit more. So look at the caveats now. So all the methodological and measurement choices affect the input. So the microphone quality, room acoustics. Maybe I'm doing one interview in the perfect insulated room, but then I'm doing the next interview in a cafe because that's where I had to meet the person, and then the audio file is written with signals from the street, from other people there. That's not going to be the same audio file. It's not going to carry the same validity. Background noise, as we just said. The compression, we're going to speak about that a little bit, is the resolution of the file, let's say. how good the quality of the measured aspects of the audio is. Pretty important. You can hear me now because of something called a Fourier transform algorithm. So what I'm talking to you, what I'm saying from my mouth is going into this mic. We're going to talk about this later, but I'm thinking about this now. So my voice comes out of my mouth, it goes into this microphone, it gets compressed, transformed into a digital signal that is carried over the internet, and you get it in your machines. It gets decompressed and then plays back for you, and your ears are registering that sound. For all this process to happen as fast as we're doing it, we need to compress it a lot. And when you compress, you lose some elements. So you need to be aware of the compression rate when you're doing it. And we're going to talk about that too. Yeah, as you said, as you extremely, very pointedly noticed, language and phonetic content differ a lot among people. Speaker identity, their gender maybe, but generally because how they speak. I know that my voice is generally very high-pitched, but there are some other people that speak with a much lower voice. So that makes a difference. Also speech rate, how fast people speak versus other people. And some of the pre-processing choice as to where we're going to cut the sound, what we are leaving out, and what we're keeping in. All of these choices, these are methodological measurement choices. They can affect our data, they can affect our input, and thus can affect our output. And we need to be aware of all of this. Some validity checks that we could be doing is think about what is the unit of analysis here. Is it the second? Is it the entire speech? Is it chunks? Or same as we do with text, basically. What is the social science construct we are trying to gauge here, to proxy here? What observable feature measures it? What else could produce the same feature? Could we have a validity check of a second nature that could validate and robustness check our measurement? Does error vary by group, by language, by party, by gender, or the recording context? And that's where metadata is very, very key. So it's really important to keep note of where the recording was took place, and have that later as a test for how the error or the measurement changes as these variables change. If you can have a small hand-coded validation set that does the same but manually as we hear it as humans, that can also be great. Same as we do with text again. And finally, it's always good practice to check at audio rights, consent, whether the platform terms are respected when we download a video to use it for analysis, when we download every video to use for analysis. So these are things we need to be aware of. Any question for these particular caveats before we start talking about what sound is? All right. So let us answer the big question. So what is actually sound? What is voice? What is speech? So I'm going to present to you a series of slides here that I've very proudly stolen from some YouTube videos that I know are out there and that are amazing. And I have the links to those videos in the last slide here, and I really urge you to go watch them because they're really cool. Anyway, basically, as I said before, when I open my mouth and my vocal cords start working, some sound comes out of it. That we've decided that we call it language and it bears meaning, etc. But before that, my different positions of the mouth cause different things to come out in the shape of waves and waves in the air that move particles in the air. So imagine this thing on the left is my vocal cords and my mouth movements. They oscillate and they move the air particles and they create waves. And on the end here, this is your ear or your microphone or a digital microphone. And as I speak, a sort of wave form is created. And this is the digital representation of what is coming out of my mouth. So a sound wave. So sound is an audio wave. It's a wave. This is a sine, something we call sine wave, SINE. That's a mathematical term, and this is a normalized wave. But you can think of audio as a grouping of all of these, multiple of these sine waves. But in essence, audio is a wave, and a wave has two. An audio wave has two very important aspects. So frequency, measured in hertz. So how many things something happens in a second. So it's something like a rhythm. And it describes the difference of wavelengths. And we interpret frequency as high and low pitches. So a high frequency wave is a wave with short wavelength. So the tops and bottoms of the wave are very close together, whereas a low frequency wave has a larger wavelength. And when we have short wavelength, is a high pitched noise, something that can really penetrate things, whereas a long wavelength is a hum, like a bass, a lower, deeper sound. And intensity describes the amplitude, the height of the wave. So the distance between the baseline and the top, and the baseline and the bottom curves of the wave. This is what we call intensity, amplitude. So how loud basically the sound is. These are the two aspects that we really care about when we're going to be measuring later on in Python as well. Important to note here that the human ear has a very set range of frequency that it can hear. So our hearing starts from around 20 hertz for the average person and ends around 20,000 hertz, 20 kilohertz. And anything in between we can hear. Anything under that is called infrasound, and we can't really hear it. We cannot hear it. And anything above that is called ultrasound, and it has the capacity to penetrate aspects. That's why in medical terms we use the ultrasound, because it can penetrate our skin and first cells. And these are high frequency and high pitched audio. We cannot hear them either. So whenever we are working with sound, maybe you can get a sound signal that is all over this range, but we only basically care about this chunk here. The rest, we cannot hear it anyway, so we shouldn't care about it. Another important aspect when we're dealing with audio as audio waves is the sample rate. Again, measured in hertz, because hertz means how many times something happens in a second. But you can think of sample rate as the resolution of the audio. So when we have a video, we're talking about the resolution of a video. So how many pixels and how many pixels per second we have. So here we are talking, sample rate is how many times per second an audio signal is measured. So a very common measurement is, a sample rate is 44.1 kilohertz. And it means that the sound is being sampled 44,000 times per second. So as I speak and the wave comes out of my mouth, the microphone can capture that sound 44,000 times per second. Obviously, higher sample rate captures higher and more frequencies, but also creates obviously larger files. So more quality in the audio means that we can potentially find more features, but then it's more heavy computationally to analyze that file. And that's the same as with any kind of digital signal, be it audio or whatever. More information means more difficult to compute. Yeah, we can, you can see here a visual depiction of this as well. So, oops, sorry. Yeah, I have some comments here. I hope you can see here. So for example, 16 kilohertz, so 16,000 hertz, 16,000 measurement per second is a very common is a very common sample rate for speech analysis, speech recognition, diarization, and many of the pipelines that we're gonna see. And it captures frequencies up to 8 kilohertz, which is usually enough for speech. So when we talk, speech is somewhere here. So all of it constitutes speech, but the important frequencies that we care about when we speak is somewhere here. 44.1 is very common for general music files. It's the standard CD quality sample rate. Most WAV files you download are probably using this. And then also 48,000 hertz is very common in films, in the cinema, podcasts, and professional recording workflows. So they carry much more, many more frequencies and more quality. But obviously the files are harder, larger, harder to play. You need better equipment to be able to hear these frequencies and play them back. So yeah, so basically sample rate, how many times we break down a wave and we measure down a wave. So this is a higher sample rate on the light, many more measurements. This is a lower sample rate. So as we said, when I have a .wav waveform audio file format, is basically a file that when I open, it's gonna play back a sound that is gonna mean something in my ears, but in essence, it's gonna be looking like this. And we're gonna see what this means now. But you should think about it as waveform. So this is waveform. An important aspect here before we continue is the Fourier transform algorithm. So it's one extra thing that I need you to be a little bit patient here and bear with me because it's kind of important. So when we get a file like this, so I say, hello, my name is Yani, and I record that and I put it into a WAV file that looks like this. Then what I actually said, and it looks like this, it actually constitutes out of many individual sine waves, like this one. So the basic wave. So multiple waves like this are gonna make the waveform that constitutes the audio file that contains hello, my name is Yani. And in order to get these individual frequencies, these individual sine waves that constitute the big waveform that we get and we hear exactly what we want to hear, is called the Fourier transform. It's a mathematical algorithm that is relatively complicated, and I'm not even sure I understand. The cool thing about this here is that the fast Fourier transform, FFT, is being dubbed as the most important numerical algorithm of our lifetime. It allows you to compress files. So it allows you to be watching me right now talking to you. The reason you can hear me and see me talk right now is because of FFT, because we can disentangle audio and video files and compress them and make them way less so that we can carry it over signals. And you can hear them, you can put them back together, and you can see a beautiful video and a beautiful and my beautiful voice is because of this algorithm. And in particular, we care about the short time Fourier transform, the STFT, which is just the same thing, but the idea is that we are chunking this into shorter times and we are doing the transform in smaller sections. So it's a bit easier to do. We don't have to do this, thankfully. We just write a very simple line in Python when we're working with data, and the machine does it for us. But you should think about the Fourier transform as, since audio is a waveform, so air pressure changing over time, the Fourier transform decomposes that waveform into the frequencies that make it up. So imagine we have this waveform. Again, credits to this amazing video from Veritasium in YouTube. I really urge you to watch it. So it turns this waveform that we have into its constituent frequencies and wavelengths. So it's very, very, very crucial, and we need that. I know it sounds a little bit arbitrary that if you put these waves together, they end up looking like this. So I have the resources here about what Fourier transform is, and I urge you to go and watch it. Just before I do that, I just want to show you a very quick simulation. So let's say we only had one sine wave, so this red line, and this is the outcome. If I were to add a second wave that looked like this, putting these two waves together, it causes the outcome waveform to look like this. If I add another frequency, it's going to change it even more. If I add more, if I add more, if I add more. And look, the waveform in the end, because I put all of these frequencies in there, ends up looking something like this, which has nothing to do with the original. So as I remove, you can see in the end, this line is going to be changing as I remove some of them. So I remove one, changes, I remove one, changes more, changes more, changes more, more, and we go back to the original. So the Fourier transform allows us to take this final waveform that we have, which looks like this, and give us all the individual frequencies that compose it. Okay, I hope it's relatively clear, but that's it for now. So is there any question around the Fourier transform for now, and what audio is, and this general introduction that we had so far? Okay, cool. So before we start with the Python Google Colab notebook, so the rest of the class is going to be relatively, not relatively, it's going to be only in Python. So I'm just going to do a quick introduction about transcription, but then the rest is going to be in Python. I'm just wondering if that is okay with everyone. Worst case scenario, you just follow along my my talks, but you guys please let me know if something is moving fast or something is not discernible and understandable. So maybe if you have something to add, please let me know. So okay, so before we start, I will talk about extracting audio from video files, but before I do that, I want to talk a little bit about transcription. So obviously, the number one thing you can do with audio is transcribe it and get the text out of it. That's like the number one thing most of us do with audio files that contain speech. And I've done this before, and we've done it a little bit also in the winter school. We can also talk about it in the summer school if it interests people. We are going to talk about some tools that are out there that provide very, very high quality of transcription, but we're also going to look at how we can do it programmatically in Python, using, again, the same state-of-the-art technology. Right now, I think I've spoken to you about this before. There's an AI for that page, and someone can just type transcription. So this is an AI aggregator. It aggregates artificial intelligence tools right now. If I type transcription, there are about so very, 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 very a lot of tools are out there for 12,000 tasks. 50,000 tools overall are here. So if I just type transcription here, it will show all the available tools that are here that do transcription. So basically, you can consider this a solved task. So automated transcription is something we have solved, and you don't really need to worry too much about quality. What you need to worry about is what tools you're using, how much you're paying, etc. So this AI aggregator allows you to just go and check with like reviews, pricing, and all that put together, and comments, etc. So it can be useful. But as I said, there are a million tools. I'm just going to show you one that is open source, that is free, and that is compliant with GDPR protection rules. Because when we are working with sound of someone's voice that has been recorded, we need to be aware that it contains, by nature, by default, sensitive data. It's their voice, it's their speech. So it can be used to re-identify the person. It can be used in many, many ways. So we need to be aware that we need to handle this data as sensitive data, and we need to pay particular attention to that. So yeah, so as I said, transcription is sort of a solved issue, and there is this tool by OpenAI, the company that is behind ChatGPT, but before ChatGPT, it was also an open source software company that built AI tools. It had built a tool called Whisper, and it has allowed it to the public. And Whisper is the state-of-the-art tool right now, algorithm right now for transcribing audio in multiple languages. It supports over 95, something like 99 languages right now, including Turkish, Arabic, Greek in my case, and it's phenomenal in terms of performance. And because it's open source, it means that someone can take it, put it in an application, in a wrapper, and sell it as a software. Or it means that you can just open a Python script, download Whisper in your environment, and just start transcribing. And that's what we're going to do. But it means that some third person here that is somewhere between, I want to make money by selling this, by making an app that I sell, and make it a fully programmable thing. I'm just going to make an app that people can use, but I don't care about making money. And an app like this is called Buzz Captions. So Buzz Captions is on the Mac Store for MacBooks, but it's also on GitHub for Windows PCs. So I can look for Buzz Captions, and on GitHub I have this post here, and down here I can install from SoundForge a .exe file, and I install it, and the app looks like this. Let's wait for it to open. Generally, it's a relatively easy app to open. So look at this. So it's just this window here. That is basically a front end, a wrapper, so a package in front of Whisper. So under the hood, Whisper is working, and this is just a point and click front end that allows you to use Whisper automatically. So basically, you click on the plus sign, you choose an audio file. Wait. Let me bring some of the files I was working on. Yeah. So this is an audio file, a very simple Turkish language, super easy 2-sentence dialogue. I'm gonna open it now. Let me know if you can't hear it. I assume you're gonna be able to. Could everyone hear that?
No, we couldn't.
No, you couldn't. Yeah, sorry. Yeah, so maybe audio is not gonna work like that. Just give me a moment. How about now? No, wait.
Merhaba. Merhaba arkadaşlar. Merhaba. Bu bölümümüzde bir tatil hayali kuracağız.
So a very basic dialogue. So I'm gonna use bus captions now. I'm gonna choose that file. It's an MP3 file. It doesn't really matter. It can be many kinds. And here is where I choose the underlying model. We should use Whisper. And here I can choose one of the 5 versions of Whisper, from tiny to large. Tiny is the smallest model, and large obviously the largest, and anywhere in between. So as we said, with large language models, with AI, more size means better quality in general. But more size and better quality means more computational power. So the larger the model, the better performance you're going to get. So you will get a better transcript, but it will also take your machine longer to run. So it will take longer for the same transcript to finish, and you get the outcome. But at the same time, there is so if we go to the just a moment. If you go to Whisper's page, which is this GitHub page, this is where we download Whisper from. This is where these guys from Buzz used, and you see the explication of the model, and you have here the model size and the parameters, how big it is in terms of how much RAM it gets you and the relative speed you get. You also get here a comparative plot about performance per language, assuming you're using the large models, right? And this is the same. So you can see that Dutch, Spanish, Korean, Italian, German, Thai, Russian, Portuguese are up here. So the least amount of error rates. So these are error rates. And here down you get Albanian, Tamil, Swahili, Armenian, Kazakh. Somewhere in the middle here we have Greek, and Turkish is somewhere here as well. Can anyone guess? I think we had this discussion before, but can anyone guess here why these languages have the least amount of error and these languages have the most amount of error? So I'm just going to explain it very quickly again. So this is a comparative plot that tells you how much error they found when they validated the model in their data. So for Dutch, only 4% of the cases were wrong. The rest were transcribed correctly. In Spanish, only 4.7 cases, 4.7% of the cases were wrong. The rest was transcribed correctly. In Albanian, almost over half of the sentences or half of the text was transcribed wrongly. So you can see that some languages here like Marathi, Belarusian, Kazakh, Armenian, Swahili, Tamil, Albanian are here with the highest amount of error. And languages like Dutch, Spanish, Korean, Italian, German have the lowest amount of error. As I said, Turkish and Greek are somewhere in the middle, but on the upper side. Can anyone guess what these languages have in common versus these languages? Okay, Omar jumped in the chat and said it basically. So indeed, these are what we call low resource languages. So there isn't enough data in the training. No, I mean there's too much training data when these models were trained. So the model has seen a lot of Dutch examples, a lot of Spanish examples, a lot of Korean examples, a lot of Italian, and it can perform this transcription more in a better way. Whereas for Albanian, there isn't enough data that has transcribed audio to text that it can learn from. So similarly, does having different dialects in a language affect the error rate? Obviously. So part of the error sources can be due to the fact that we have trained a model to capture the mainstream accent, let's say, but then you go to some peculiar village in Greece to interview someone, and they have a very, very hard, strong accent. The model might not do as good of a job to transcribe that peculiar accent versus you, versus the mainstream accent. So that's a great comment. But it doesn't have to do with the fact that we have more accents in one language or the other. This has to do with the fact that we haven't had enough training data transcribing, connecting audio to text in these languages here. The takeaway here for you, the important thing is that when we are transcribing and we are choosing a model to transcribe, if we are working with a language that is on the lower end of this table, we should increase the size of the model. We need a larger model for a language that is higher error prone, more error prone. So when you're lower on the table, we need to go higher in the model. When we are up in the table, we can get away with a smaller model as well. So when we're talking about English, for example, we can easily go with tiny when we transcribe. If it's simple, if it's a clear audio file, and we know that the audio quality is great, they don't have a peculiar accent, we will get away with tiny and base. But as we go to a lower research language, or as we have like weird accents or background noise, we should go for a larger model. For the sake of demonstration here, I'm going to go with base, and I'm going to transcribe that quick Turkish audio file that we had. And I can also choose the language. I can go with one of the languages, the 99 languages. I'm going to choose Turkish here. And I'm going to export it as txt. And I'm just going to hit run. So now this file is queued here, as you can see. And it's going to take a while, and we're going to check the transfer. Oh, well, actually, it's going fast on my little Mac with the base mode. So it completed in 15 seconds, basically. And now I can see the transcription that says, I don't know if you can see, but I think it's right, or maybe this is not right. I'm gonna put the audio again just for the sake of hearing it once more.
Merhaba arkadaşlar. Merhaba. Bu bölümümüzde bir tatil hayali kuracağız.
Would you say this is a good transcription or not? I'm gonna play it once more.
Merhaba arkadaşlar. Merhaba. Bu bölümümüzde bir tatil hayali kuracağız.
Tatil is wrong. Bu
Okay.
bölümümüzde bir tanrıtıllı hayali kuracağız. It has been transcribed.
Yeah. So it's not perfect. It's not perfect in terms of spelling here, or is it outright wrong?
Yeah, this is a totally different word.
Okay.
Tanrıtıllı.
So while we're waiting, I'm gonna choose again, and I will go with a small model. Yeah, and run it again. So previous one took 15 seconds. I guess this is gonna take over a minute. And we're not gonna wait for this now. We're just gonna continue. I'm gonna evaluate it later. Well, not super slow. Maybe let's give it a moment. Let's see what's gonna happen. I'm gonna wait for it. So 30 seconds, not that bad. Actually, we could go higher if it's that easy. Well, I mean, it's a very short audio, right? How about this?
It's perfect now. Bu bölümümüzde.
This is perfect, yeah. So in this particular scenario, I mean, okay, very clear, very easy language, nothing complicated. But you could see that we could get away with we could get away with a smaller model. So we went with a middle one. But if the case was more complicated or the language, we wouldn't be able to get away with anything smaller than large. So it's something we need to worry about, to care about. So Buzz can work offline. So I could just shut off my Wi-Fi connection here, and it would still work. This is not an online tool. This is not a cloud tool. So I could be on the field taking interviews of people and immediately passing them in Buzz captions and getting a transcript out. This is a very helpful tool for transcription on the fly. And because it works offline and doesn't require any account or internet connection, it's also very secure. So everything stays in your machine, everything happens in your machine. And it's a very helpful tool. So with that said, yeah, we got Buzz covered. I think we should take a break now and be back at 15 past to get started with the Python stuff. Is there any question at this point, maybe before we stop? Just give me a moment. Let me stop sharing. Right. So are there specific caveats for diacritic sensitive transcription for languages like Arabic or Vietnamese, where diacritics dictate vital phonetic and semantic meaning? I assume that word level transcriptions that are more widely available are not enough, and rather than phonological transcription, that phonological transcription is needed. Okay, that's a great comment as once again, Omar. Thank you for the question and for participating. I just want to say that it is true that majority of the tools that we have at hand have been developed for Western languages, especially English. And Greek has been for long very hard to language to work with. And I'm going to speak for that because I haven't worked with Arabic or Turkish for that matter, but I've worked with Greek, which is does have diacritics. I mean, not even close to Arabic or Vietnamese, as you point out, but it does have some things that matter, especially for audio. So in those cases, the advent of LLMs has helped a lot. So the fact now that we have these world knowledge models that have seen tons of data, including in these languages, however lower resource they are, still there is a lot of data that these models have seen. So they've mitigated some of these issues. However, anyone that works with transcription on a very peculiar language that is low resource and has some very peculiar aspects that they care for, I would argue that they are in a much better spot if they fine-tune one of these models to their particular data. So basically they prepare a subset of their data, they transcribed it manually, and then they feed that into the model to fine-tune it and make it better. I see no other way, basically. However mitigated some of these risks are, they are still there. So yeah, in my eyes, there's still a lot of validation. Like there's a higher validation bar that studies that look at these languages need to pass, if that makes sense. But you will not know before you try. So fine-tuning would be recommended upon the existing models. Yes, that's what I would say. Again, depending on the case, obviously you start with a base model and you evaluate its performance. If it's good enough, you have no reason to go with the extra step. But if the performance is not good enough, which I assume could be the case, then yeah, you should be fine-tuning. You're welcome. Anything else right now? Okay, so let's say 20 past then. So 12 minutes more, if that's okay.
Sure.
So let's continue with the second part. If you could please go to the Google Drive folder that I shared with you, and there just double click on the second file, the Google Colab notebook, and you should be seeing what I see, assuming you have a Google account, but maybe, yeah. In any case, you're not, yeah, thank you, Sumaya. You don't have to follow along as I do. You're welcome to just simply look at what I'm saying. We're not going to be writing any code. I'm just going to be explaining a little bit what the code does. I don't think it's within the scope of this workshop to just write code. And it's also, I'm also not 100% familiar with all of these packages. So in any case, I mean, I'm happy to answer any question, but I think the cool part here is seeing how easy it is to do some of these things in Python and how few lines of code it takes. So before we start, just if you want, as I said again, you just follow me here. This is Google Colab, just very briefly for those that are not aware. Maybe this is a little bit redundant, but I'm just gonna say it once more. Google Colab is just a notebook that allows you to run Python on their servers. So this what we're going to be doing, and if you clicked on this and you're doing as well, is going to run in on Google server, and it's an easy way for us to share code and work on the same on could be the same file. Now we're just working on copies of the file, each of us. So if you make a change here, it's going to be a change for you. And if you refresh the file, because this is my file, you're gonna keep getting the same file. So if you want to work on this and make changes, just remember to copy the file entirely. You can download this and open it in your own environment as a IPython notebook file as well. But for now, let's work on Google Colab. So first of all, there needs to be a green tick mark here, which means that the instance is connected. So you're connected to a machine with RAM and a processor. You could change the runtime to add GPUs, but you need a better account for that. Maybe if you click on, so I clicked here and then change runtime. And here you have these options, but if you don't have a pro account, like I do, probably you don't have these options. For now, what we're going to do is going to be CPU based. But as we increase the size of our data set, the size of our files, the audio files, the models that we're using GPUs is sort of obligatory, because you need the acceleration that you get in computational power with graphics processing units and not central processing units. In any case, what we're going to show today can all work with a CPU only machine, but just bear this in mind. So the very first thing I need you to do is click on this play button here. It's going to pull some data from my repository, and if you click on the files folder here, you're going to see this. After you run this, you're going to see this LLM workshop file where it has some files we're going to work on today. Okay. You're also welcome to just pull up your files if you're working on some audio files you want to test, but we're going to do that later. So first of all, let's speak about extracting audio from a video file. So I have a video file here from the European Parliament, which is a .mp4 file. I'm just gonna quickly download it so that you can see it. Yeah, it looks like this. It has a small intro.
Seconds, please. Stick to the time. Mr. Doherty, 30 seconds for the answer.
So thank you for the question, and I'm not really sure I agree with the sentiment that you've outlined. What I have seen for the last 14 months is collective parties trying to work together in order to solve a problem for all of the people in all.
So anyway, the audio itself is not, like, the content is not that important, but see, we have like a video of a speech of an MP that we could analyze for their movement of hands, etc. But we are gonna be looking at the audio file. So, okay, this is not a particularly interesting speech anyway, but the interesting thing is that there is an accent here, an Irish accent, sort of heavy. I don't know if you noticed, but anyway, it is there. So let's say you have a collection of videos like this, and what you want to do is you want to extract the audio from them. There are many tools offline that do this, but the point is for us to do it in Python programmatically, so that if you had like a huge collection of files, you could loop over that with the same script and do it fastly. So to do that, we need a package called MoviePy. We don't need to install it because it's already in Google Colab by default. So from MoviePy editor, we are importing video file clip. So you can run this here. Take a few seconds and it's done. And now we are specifying the path to our file, and we are calling this video file clip, and we're putting everything into this video object. So I can go to my file here on the 3 dots and click on copy path. So again, if you had a video that you wanted to work on, you could as well just pull that video and put it here, and it would be uploaded, and then you could work with it as well, just on Google Colab. This is not the best way to work when you're alone, but if you now want to test this on your own, you're more than welcome to, and I would be happy to answer questions on this. But let's work with our file. So we are calling this function that we called on the Doherty clip, this video file from this European Parliament member, and we run this. This is only on CPU and a 30-second video, but it was analyzed within 1 second. If you had a GPU and the video was long, if you didn't have a GPU and the video was longer, it would take more. If you had multiple videos, it would take ages. So if we could have GPU, we would have added an argument here saying use GPU acceleration, and it would have been even better. So now, from this video object, we are pulling the audio aspect of it and putting that into a new object called audio. And we are also writing that file now into this path. So we're going to create a new extracted audio.wav, and this should be placed somewhere here once I run this. So it took a few seconds. Yeah, and now we have the extracted audio file, and from that I can also import this really cool module to play audio files on the Google Colab, which is called IPython display, and I import it as IPD, and then I do IPD.audio, and it creates this little snippet here that I can play for you with that file that I just created. So this extracted audio. And this snippet here, so now I can, let me turn to the speakers again. Have this initial intro with no audio.
Seconds, please. Stick to the time. Mrs. Doherty, 30 seconds for the answer.
So thank you for the question, and I'm not.
So as you can see, it's the same, the audio from that video file that is now playable here and analyzable. And it's stored in this audio object that looks like this if you run it on its own. There are other information I can extract from a video. I mean, these are a bit beyond the scope here. This is not a workshop on analyzing video, but with this Python library, you can also extract the duration of the video, the frames per second, size, if it's rotated, etc., and other metadata that could be useful and could complement the audio signal that you extract. Any questions about just simply extracting audio files from video? No. Again, as you can see, very, very simple step. Imagine you had multiple of these videos, you would have them in a folder here, and you would write a for loop that goes into them and extract this audio object and creates the WAV files that you will then work on. Cool. Now, let's go back a little bit to transcription. as we said, we work with, I showed you how to transcribe with Buzz, which is a tool that uses Whisper, but now I'm going to show you how to programmatically access Whisper and how to run this transcription on your own in Python programmatically. First of all, we all need to run this line here that pulls Whisper from GitHub. This should take around a minute, so please click on this. It's gonna take a while to pull. In the meantime, I'm just gonna click on the Whisper page just once more, just to show you once again the idea behind these models. The fact that the larger the size, the better the performance, so you get a better transcription, but at the same time it takes more resources to compute. If I'm on a Google Colab notebook with a lot of resources, with high RAM, a T4 GPU, etc., this is going to be fine. I can use the top model all the time. That's not a problem. But if I don't have those resources, the large models are going to take very long to run, and this is something you need to be aware of. And keep thinking. Sorry for insisting, but it's very important. And one more thing here. Yeah, I think we don't need to spend more time here. This should have run. Okay, so we import Whisper and OS operating system just to load the files we need. So Whisper is imported. How do we use now? So the package Whisper is imported, not the actual model itself that does the work, not the LLM that does the work. To do that, we need to call Whisper, the library, and that load model. So, and then we specify which kind of the 5 models we want. So let's start with Tiny, and we put it in an object called model Tiny. So I run this. It's very fast, only 17 megabytes. So that we don't wait, let's also load model, let's load model small as well, which is, so we go from tiny to base to small. Small is in the middle, so then we have medium and large. Let's also load small as well. That's 460 megabytes. So you see the jump. Okay, and now we are gonna call the model object, model tiny, dot transcribe. It's as simple as that. And in here we just pass the path to our file. So we can use this extracted audio from the Doherty app. Well, I made it work with MP3. Let's hope it works with .wav as well. Can ignore this warning. So it's now transcribing the speech of that MP, those 30 seconds. Let's give it a moment. While we are waiting, it shouldn't take much longer, but while we are waiting, you can also, in this dot transcribe function call, okay, it worked. I'll continue just in a moment. So now I can take this result and focus on the text object inside it. And if I click here, I can see the transcription that it did from the WAV. It's really bad, actually. Okay, this is terrible. Let's play with this audio file, this Okay, it's the tiny one. Let's try the, well, no, it's gonna take a long time. So let's not wait for that. Let's change back to the test audio English, but just for the sake of you seeing what that file looks like.
Hey there, this is a quick and silly video to allow you to experiment a little bit with the process of transcription on YouTube.
Okay, again, nothing really serious. Again, I don't think it's the best quality of audio, but it should be a bit better now. So we call model tiny on this. So while this is running, again, it shouldn't take too long. You can also specify, okay, it worked the moment I started speaking about this. So hey, here, there, this is a quick and silly video to allow you to explain. I'm pretty sure he said, hey there. Also looking for you to do here, I think he said, all I'm looking for you to do here is to use the YouTube tool. So you can see that the quality of the model tiny is kind of bad even in English. So I'm going to use model small here and go back to the previous file. Sorry, extracted audio. Cool. And run the small on it, and we will see what happens then. Let's see if the MP's speech is going to look a little better now. Anyway, while we're waiting, you inside this transcribe function, you can also specify the language that you want the transcription to happen. If you don't specify, it's going to be in English. And if you have a text if you have an audio that is in any other language, it's going to automatically translate it to English first. So if you pass an audio in Turkish and you don't specify the language, it's going to try to transcribe that in English by translating as well. So it's pretty crucial to specify language. So we would do it the same way. So model small transcribe, but just in the end, we're going to add another argument called a TR. So I'm feeding here the Turkish audio sound we just heard, the quick and easy one. And well, we have to wait for this to finish first. Let's give it a moment. So you can see now just jumping from tiny to small already makes a difference in running this. And this is because we're running it on CPU also. If we were to do this properly, we would do it on a GPU and it would be much faster. Also, you can be 100% certain that Google is not offering you, because this is the free version, it's not offering us the best, the top performance in terms of CPU, and it's prioritizing potentially other calls from other people as well. So there's also this aspect. If we were to be running this code locally on our machines and not on Google Colab, it would be much faster. It's taking way longer than I expected, and I'm also a little curious if .wav makes a difference versus .mp3, because all I've tested so far has been with .mp3 and the results were great. So with .wav, maybe there is some other issue, and that's beyond the model's quality. While we're waiting a bit, just want to show you. I believe this is the correct transcription of what we had before, right? the small Turkish sound. So I think there was a mistake here, but this is big. So when I run it before, by specifying the language, even with the base model, so not the super tiny, but this one and this one, I got the correct result. So it worked fine. I think it's taking a bit way too long, so I'm a bit worried now that something else is happening. So I'm just gonna interrupt this. And yeah, let's run this on the Turkish text and see how long that takes. After that, we're going to speak about speaker diarization. So the idea that we okay, look how fast that was. I mean, I think there's an issue with the .wav file, so we have to figure that out. Anyway, so the model small on the Turkish sound, run very fast, and yeah, it's basically it is the same. I mean, that's what we expect. So imagine you run this in a loop, multiple files, it goes over your file, and you transcribe it with Whisper like that. So let's speak about speaker diarization. So for those that don't know, speaker diarization is the idea that together with this little text, we also ask an algorithm to figure out if there is a change in speaker, how many speakers are participating, and also when does a speaker speak and until when. And we ask it to also label its text. So in that particular video, this sentence was uttered by one person. This merhaba here was uttered by a second, because they are two people in a cafe speaking basically. And then sentence was uttered by a third one, the first person again. So ideally, we would like a transcript that says this text belongs to the first one, this text belongs to the second, etc. And we would use that. Speaker diarization is also what happens in subtitling movies and films in general. So there is someone that has connected the audio file with the subtitle, so that the subtitle appears on the right moment when someone is speaking, right? But here we also care about identifying a second speaker or a third or a fourth if they are there. So with speaker diarization, we can do that. In order to do it, we rely on a Python library called WhisperX. So it's another wrapper around WhisperX that uses the Whisper technology to do the transcription, but then it uses some additional libraries, including this Pyanote pool of tools and models, and the speaker diarization community model that allows you to do all the pipeline of diarization. That includes a lot of steps, to be honest, and those steps include alignment, so figuring out exactly at which point in the video, in the sound, the text should come. These are not trivial tasks, and they're all handled by this library, and it's phenomenal. Again, there are transcription tools out there that are paid, and they do speaker diarization, but the majority of tools, including Buzz that we saw before, does not do speaker diarization. You only get a script, a text of the entire spoken thing that was out there. I just want to say here that in order to get WhisperX to run, so as I'm speaking, maybe we should run this because it's taking a couple of seconds. So you can click on this cell here. So before we start, in order to use this Pyanote from Hugging Face, and remember, Hugging Face is this repository for models, for artificial intelligence models, but models in general and LLMs. You need to have an account on Hugging Face, and in your account, you need in-access tokens. Sorry, pass this. You need to create an access token and copy it into the notebook. So you go to secrets here, and you add the value here. I just want to know if you guys open this My Notebook. Do you have this value here already? Can anyone check and just put a check mark if that's the case? So here on the left side, you click on this key arrow. Does this appear here already with my token, or it's empty? All right. So if it's empty, then we all have to do the following, which is again, this is only if you want to follow this. So I'm gonna do it together with you. So here we click on the I pasted a key here that you can copy and use in the chat of the Zoom call, and you need to copy that key and come here to the secrets and click on add new secret, name it HF token underscore HF underscore token, and in the value you paste it in there. Yeah. You also enable notebook access by clicking here. And you can close this, that's okay. So let me, there's a small issue, I'm sorry for that. If you have tried and you have the token here, then great. If not, again, just look at what I'm doing in the screen. It's not that important that you follow. I think there was a typo here. There was a Y here. Yeah, so Ali Osman, it's just above your text. So in the chat, so name should be HF underscore token, and the value is just this text that I copied and pasted in the chat in Zoom. Is there anyone that is still trying to do this and hasn't done it? So by this, I mean adding the Hugging Face token here. Okay, I assume that no one else is doing it. So if someone is trying to run this cell here, there was a small typo here, and instead of Python, it said Python. It should be Python. So just remove that and run it again if you wish. It should be done very soon in my case. The reason we're having these lines, and I'm not explaining them, is that WhisperX requires a couple of packages, which are all of these here. And when we are working in our own Python distribution, it's very easy to do. You just install one by one and it's very easy. But in Google Colab, some packages are already come pre-installed. And when you try to install WhisperX, it doesn't work. So because we are in Google Colab and because there are these limitations, but we need all these dependent libraries, dependent packages, we are creating a virtual environment, VN, and we're running Whisper inside that virtual environment that contains all the applications as we expect. So please ignore this. It's not that important, but if you want to continue, this has to run. So if you want to follow along, this thing needs to have a check mark and this needs to run. And also here, the HF token is being used by the notebook from here. So what I do after that is I'm running this line of code, this couple of lines of code that runs in the virtual environment, basically run Whisper. And what this does is it takes the path of the file. So in our case, this English Basic Convo 2. Let's hear that for the sake of seeing what it is. Oh, yeah. So just very quickly so that you can hear it.
Hello.
Hello.
What is your name?
My name is Calvin. What's your name?
My name is
Okay, very exaggerated, easy, basic English conversation, but you can see there are two speakers. So what I want to know, I don't just want a quick and easy transcript of this. I want to know when each speaker speaks, okay? So when I run this and I pass in the English Basic Convo.mp3, I specify the language as English. I'm passing my Hugging Face token because it's going to be needed. I'm asking it to diarize. And because I could also skip this and not get diarization. And I could also, I am specifying the model I want to use for the transcription. Here I'm using Whisper's base. I could switch this to tiny. I could switch this to tiny or small or whatever. But base should be enough here. Device CPU, again, if I had GPU, I could make it faster by putting GPU here. And because it's CPU, I need to also specify the compute type to be integer 8. Just let's not dwell too much on this. And then for the alignment thing, putting things together, we are using a wave to vec2 model. This is again a model on Hugging Face. We can just check it out very quickly. Oh no, this is for Russian, but there is one for every language basically. But there's also the generic one, and this is putting together the text, the audio, and the text when it needs, and it does that by seeing a lot of text. So obviously it makes some mistakes, but in the majority, this is what we use to do diarization. And then I also specify an output directory where the file is gonna go. So there is no output folder here. Once I run this, I'm gonna see the output file and it's gonna take a while to run. So we're running with base, which remember is the second smallest model. Let's see what this does now. Remember, this was a very quick conversation of 15 seconds about basic English convo and good mornings. So there is some output here that can help you see what's happening, but I mean, it's not that important. The important thing here is you have the transcript already. hello, hello, what is your name? My name is Calvin, as the person said. What's your name? My name is Camille, blah, blah, blah. Okay, this is the transcript, obviously we care about, but we want to know when each person spoke. So the alignment and diarization is the key part here. So let's wait a little bit more. So now performing alignment is taking place. Give me a moment, Ali, and let's figure this out together. From Google Colab, import user. Yeah, so it shouldn't say secret name. It should say HF token. An HF token should be the name that you have here. So I don't know if I'm making myself clear, but feel free to open your camera and let me know too. So the thing you pasted here in the chat says secret name. If it says secret name, it's okay, but you should put secret name here. Mine says HF token because I have HF token here. I don't know if that makes sense. But we're not deleting it. We need this, otherwise the rest is not going to work. We need to tell Google what token to use from Hugging Face so that it can use Whisper. But please don't dwell too much on this. Let's see what happens actually. Let's see what it does. And we can also, I can also take questions like maybe not right after the end, but we can also do it at another point as well. So maybe we can discuss. So now these lines of code here created this output folder that contain a couple of files, which I don't know, I guess you've seen before, TXT file with a transcription. But what is really important in my eyes is this SRT file, which is what we have for subtitles. I don't know if you, like back in the days when we were streaming, before streaming movies, we would spend hours downloading a huge video file of a movie and then also look for subtitles in our language, and we would put them in a software that put together in the right moment of time. And it needed that SRT file. So now if I click this SRT file, it looks like this. So speaker 0 at this point in time started speaking and stopped here, and they said hello. Then speaker 1, the other speaker in the file, started at this second, stopped at this second, and said hello as well. Then the first speaker said, what is your name? And so on and so forth. I don't know if you see here, but if you see the point here, but this is extremely, extremely crucial to have. Let's say you are focusing on who speaks when, who speaks on top of someone else, how long they take to say a phrase, turn taking, all of that stuff is very, very crucial. And you can only do that with speaker diarization. Now I can use this script and write a very small function that would only give me back what speaker 1 said. So it would take only the bits that have speaker 1 on the front. So I get only the text of one person, not both. Maybe I'm only interested in one text, not everyone's utterances, right? So even just for disentangling, you need something like that. So 2 more blocks and then we are done. Imagine you would have multiple audio files. So I have here a couple of MP3 files, and if I use glob, I can see all of them. I can list all of them, all MP3 files. I can now write a small loop that for every MP3 file in MP3 files, I can do the exact same line of code for all of them, but instead of specifying one path here, I'm just telling it just use the path of this MP3 file you're working on right now, and the rest is the same. So because it will take a while, I don't want to actually loop on all these. I will just loop over 2 just for the sake of me showing you what that looks like. I'm just going to loop over basic combo 2 and test audio English, this file. I also have Tiny again, just for the sake of this being a bit faster. But imagine you had a ton of files here. All you need is these 10 lines here, and it would go over them, and you will have these perfect transcripts, or close to perfect transcripts. Very key thing here is that, as with anything in science, we need to validate, and transcriptions also need to be validated. So what scientists do is they take a sample of the transcriptions, and they have manual people listen to the file and look at the transcription and look at random places in the text and check if the transcript was right. So we need that as well. I actually forgot to put this here. So it is going through all the files, all 5 of them. And I mean, we could wait, but I don't think we should. In any case, let's wait for this bit. Now it's here. Another thing is that here, I have added one argument that is not on the top. I have added this output format SRT. So instead of having all of these files every time, the JSON, the TSP, the TXT, which I mean are basically similar. They contain similar information, but just no timestamps. I think SRT is the most useful one, because it contains the timestamps as well and the labels of who said and what was said. I mean, there's also the JSON file, which does the same as well. So I think either the JSON or the SRT are the most useful files for the next step. So you can specify exactly which of these files you want, and the model will produce only that and not the rest. So in this case, we're asking it to just give us the SRT files instead. So almost there. One more left. Now we're gonna take a break. Should be very, very fast now. There, almost done. Ali, did you make it work? Ali. It's okay if not again. I would just like to also, okay, perfect. Good to hear. I would just like to ask if anybody in the room out of the participants is working already or hoping to work with audio data. If there's someone that would like to share their case, that would be great as well. This is almost done. Okay. Sumaya, do you have a project in mind with audio?
Not there yet.
gonna stop this. I think we should be fine. Yeah. Let's refresh. So we have this SRT output folder now that we created by just specifying that this is the output directory we wanted to focus on. And if I click here, I stopped it at the 5th, but we have 4 already here. And you can see here the same file again. We can look at another English file with, it was the other one with only 1 speaker. So we got only speaker 0 here. And let's see the Turkish one. Well, this didn't work because remember, we specified language English here. And it translated, but with the tiny model, I think it's already like a really bad model, like a small model, not good one, in a low resource language. And we also asked to translate. So there are many things here happening. So if I were to do TR and went for, let's do small maybe. And I will leave this working just for the next, until we go for a break. So 1 and 2, I think is the Turkey one. Yeah, okay. So if I were to do it like this, TR and small, I would argue that this is going to be a bit better, but we'll see after it's done. Okay, so what we showed so far, and then now we're gonna take a small break. I think only 5 minutes is enough, if that's okay. What we've done so far is we looked how to extract audio from a video file, and we also looked how to transcribe audio in Python with Whisper, but also with Buzz with an external. So you are more than welcome to just add a file on Buzz Captions and get the output and put it in a folder, then do it again and again manually on your own. That's going to work as well. But if you want speaker diarization, or you want this to happen automatically, you leave your machine working and etc., then you need to access it programmatically, like the way we showed you with Whisper X. So let's see now. Maybe it's gonna Well, it didn't recognize that this was another speaker. So the second merhaba comes from another speaker. I've seen the video. So if we have to go with a bigger model because the difference in the pitch is not that obvious, or it needed a longer audio to figure out the difference in the pitch. But yeah, let's take a 5-minute break only. So, well, 15 past now. Let's be back at 15 past. I will start on the dot. And we will focus on working with an audio file now. So beyond transcription, let's see what we can do with an audio file, okay? Let's take a quick break. See you in a moment. All right, let's continue with the last part for today. We are gonna now look at working with digital signals, like a waveform, the wave that we discussed. So basically, we're gonna be working with this thing here, okay? So let's import some libraries that we're gonna need. And
Could you share your screen, please?
yes, of course. Thank you, Sumaya. Sorry for that. Right, so let's import these libraries here. So go ahead and run this. And we are going to be quickly working with this dataset called the RAV-DES emotional speech audio. This is a ton of audio files from actors speaking to the same microphone receiver from the same distance, saying the same phrase all over again with different emotions. So one scared, one angry, one normal, etc. So if I have linked to this data set here in this data frame. Obviously, I kept only 4 actors, two male and 2 female, just for the sake of us looking at it. And you can play this sound. So let's hear the first one just to see what it sounds like.
Kids are talking by the door?
So a little bit surprised. Then we have this.
Kids are talking by the door?
Wait, no, that was the repetition, I think.
Kids are talking by the door?
Sorry, I keep playing the same thing. My bad, sorry.
Kids are talking by the door?
And now this one.
Kids are talking by the door.
So the same person, but they're saying it in a little different way.
Kids are talking by the door.
And we keep going, it's gonna start changing.
Kids are talking by the door.
So kind of funny and relaxed. So basically different emotions in language, but you can see it's the same person. They are actors, obviously, but voice and the way you say something does carry meaning. And the point is how could we capture that? So to work with audio files in Python, we're using a library called Librosa. That's like sort of the default library for working in Python with audio files. It's very, very helpful and can do a couple of things. So the first thing we need to do, let me just increase the size a little bit here. So the first thing we need to do is to get that waveform that we discussed. So basically this thing here. And also the sample rate. And we do that by loading our audio file in Librosa. So we're going to work with the first one, which is this one here. Let's hear it one more time.
Kids are talking by the door.
So kind of angry, kind of like intense, let's say. So let's play with that. So with Librosa.load and the path to the audio file, you can replace this with your own if you wish. Just upload it here and just move it there. We can have a couple of information. So we have the sampling rate. So this is 22,000 slices of audio per second. That's the resolution, if you remember, the total overall quality. How many samples overall we got? 86,000. So this is like a 3-second thing. So 3 times 22 gives us this 86. And the duration in seconds. Then with pandas, we can also plot this waveform. And we can do like a very basic plot of the waveform in this manner here. And you can see that as samples go by, so on this axis down here, the horizontal axis, we have samples. So you can replace that with seconds. We have 86,000 samples. As the samples go by, we see what audio we get there. But we can also trim this. we can cut it so that it's we remove the silence if we don't need it. And I can do waveform trim this time, and Librosa effects trim waveform, and then plot it again. So we are doing the same thing as we did here, but now we're trimming, and we're leaving this empty because we only care about the trim aspect. So if I do this trimming here, I'm getting a smaller section from 0 to 6,000, whereas this was from 0 to 8,000, but still a lot of, let's say, silence is still in the audio file. So what I need to do is I need to have this top decibel argument that I can put here, and I can specify how high this should be. So if we put it at 20 and run it again, for example, now we're getting a slice of the audio that's much closer to where the action is happening, right? From 0 to 40,000 now. We almost cut it in half. And we can also slice this waveform on specific samples. So if you go from the 30,000 to 31,000, I guess, and we run this, we get a wave that looks like this. So it's just a slice somewhere here. So it's a slice somewhere here. So, okay, we've seen the waveform, but what can I do with this? So basically remember that this waveform here contains all the various frequencies that we care for. But when they are put together, they look something like this. So for example, if I do an even smaller chunk, it's gonna look like this. And if I do an even smaller chunk, it's gonna look like this. So this is a waveform. So this is what we were talking about earlier, which was this thing. So now we can also disentangle that. Before we do that, we're gonna do the Fourier transform later. But before we do that, we can also calculate some basic audio metrics about this file, the entirety of this file. Two of the most important things that people calculate in audio is the root mean square energy and also the pitch. So fundamental frequency, or F0 also is called. So the root mean square is a measurement of the average power, the average amplitude of the audio signal. So how noisy it is, how much noise it makes. And Librosa, to calculate this, takes the waveform, divides it into some short windows, as we see, and calculates the energy for each window. So and then gives you a mean value for it. So basically, if we do Librosa feature now, because we're extracting feature from the audio, and we do the RMS, root mean square, and we feed the waveform here, we are getting this array of values that contain the noisiness, let's say, of the audio file. We can see that it calculated 169 frames, so it split it in 169 frames. You can also play with this. You can make the chunks smaller or larger depending on what you want to do. And we can see that for this file, the mean RMS is 0.02, and we have like a standard deviation here. I don't think it's super important to look at that. And I can also plot this RMS now. So I can see how the loudness of the file moves as we go. So somewhere in the middle is where the person, or at least this audio, spoke the loudest. It was at this moment here that it was the loudest in this audio. But then you can compare these plots of various audio files and check with diarization. You can check exactly what was said at this point that the decibels were increased, and figure out when each person increases their decibels. So it's one metric that we can use to check something like emphasis that in the paper I showed you earlier they do. So after root mean square, we can calculate pitch, or what we call what they call, I guess, the fundamental frequency. So the fundamental frequency represents the frequency at which the vocal cords, the vocal folds of people, so what we have inside our mouth, vibrate during speech or singing. So out of all of these frequencies that we get, there are a collection of some of them that correspond to speech in particular, to singing and speech in particular. So like if I make a very weird non-vocal, non-language sound, it's not going to register within the fundamental frequency. And generally, this is like a crucial aspect of voice production. Like it determines how you perceive my pitch of my sound when I speak. So if I have a higher voice, generally, the fundamental frequency is going to be higher. If I have a deeper voice, the fundamental frequency is going to be lower. So this is a quality feature characteristic of the way I speak. And by looking at the fundamental frequency, we're looking at speech or singing only. So to calculate pitch, we estimated using the PYIN function of the Librosa package again. And when the pitch cannot be detected because either it's too low or it's outside the scope of the speech and singing frequencies, the model returns NA values that we have to remove, but we're going to do it later. And to do that, I'm calling Librosa PyYIN, and I'm creating 3 objects that are obligatory here. The F0, which is the value I care for, and 2 more that are not that important, voiced flag and voiced probability. Like let's not worry about these for now. Let's ignore them. So I'm feeding waveform there. This is the same thing as we fed before. This is the thing we're working on. And here I'm specifying the minimum frequency and the maximum frequency in between the fundamental frequency lies. So I'm telling the model that it's in between these 2 values that I want you to care for. And this is a relatively standard thing. So we call it C7, it's a note, or C2, it's a frequency quartile. And if we look at what this looks like, for C7, it's 2000 Hertz, and C2 is 65 Hertz. So we're transforming a note here to Hertz. So these are the values where we have this discernible speech. But this is a relatively arbitrary decision. We can increase or decrease these values depending on the overall pitch that we have in our data set. Maybe all of our recordings took place with a microphone that increased pitch for some reason, and we want the model, the Librosa package, to only look at those frequencies that were not affected by this. So setting the minimum and maximum can be crucial. It is arbitrary sometimes, but these are pretty standard values that we use, 65 and 2000. And there are many manuals that tell you which way to go depending on what you need. So I'm gonna calculate the F0 here, this fundamental frequency. Again, by default, it split the audio to 169 frames. I could as well increase this, but by default it sees that the overall sample rate, the resolution of the file, and it makes an arbitrary decision. But I could also specify how many frames I would like. And the F0 fundamental pitch looks like this. So empty in the beginning, then the person is starting to speak. Empty again, and something happens at the end as well, which we don't know what it is, but maybe it's because we trimmed it there. But anyway, so we have to remove these NAs because we want to calculate the mean, and we cannot calculate a mean with these NAs here. So there's missing values. So I'm simply removing here with NumPy. I'm removing when it's NA. I'm just removing those. And now from 169, we drop down to 63, and I'm just printing the first 10 values here for you to see. It's not like a big deal. So now I can calculate the mean pitch of my audio file. So I can click here and see that if I do NumPy mean of all the F0 clean array that I have, I'm getting a value of 339. On its own, it doesn't tell much. It also doesn't tell me much at all. So just getting a mean pitch on its own, I'm not caring so much. And I can also plot it over time in the file and see that it's in the beginning that the pitch is higher, and then the file goes down. So we can try to hear it once again, maybe.
Kids are talking by the door.
So I guess the pitch is very high in the beginning, and then the voice becomes a bit lower. So I'm gonna just play it once more.
Kids are talking by the door.
So kids are talking by the door, and then it goes down. So it feels like there is some aspect here of the voice being higher in the beginning. Anyway, as I said, on its own, this doesn't tell me something. But when I'm calculating this mean pitch, this mean F0 score for all my files in my dataset, then in comparison, one in comparison to the other tells me a lot. And I will show you what we can do with that. But just before that, just think of root mean square and pitch as two things that are helpful. They are different, but they can be helpful. So root mean square is about how much acoustic energy amplitude there is in the signal. We often interpret this as a proxy for loudness. So how intense someone is vocally, or like how much force they use in their speaking. Ideally, we would have a benchmark of them speaking normally in their private lives, and then see the vocal intensity and see if they speak more or louder. On the other hand, pitch, fundamental frequency, the F0 score, as we said, is generally about how fast the vocal cords vibrate. So in speech terms, it is interpreted as the highness or lowness of voice, okay? Some people speak more highly, and some people speak more lowly. But then when we put emotion or emphasis in something we're saying, these values change compared to our standard values, let's say. Yes, Aziz, please. I think we have a question from Aziz. Please open your mic if you want, or write it. Yeah.
Hi.
Hi.
At first, I couldn't unmute myself. I think I should, like there should have been a permission. Now I can speak. So my question is, since we want to compare, like, for most of the cases, different like sounds from different people, for example, do we need to kind of normalize the audio file, like the data in the audio file, so that we can compare? Is there any normalization, or is it irrelevant in this case?
Yeah, no, that's a great question. So again, there are two normalization steps. One happens when we specify when we specify this the minimum and maximum frequency we care for when we calculate pitch. So basically, again, this is what we do here. We tell that majority of people demonstrate their pitch in these frequencies. So I want you to be in these. But let's say for some reason you have a data set of only very low voiced people. You would have to make this minimum frequency a bit lower than 65 hertz, because just some people speak, some language, or maybe some people they speak louder in lower voices. If you have a group of people that consists only of people like me that generally speak in a more higher voice, you would have to maybe raise the F max a little bit so that you can incorporate all of them. So one normalization happens here, but then statistically speaking, when you say normalization in the statistical notion, you can do that once you have all the files there, so you need all your data there. You cannot do it on one file. There is no normalization pipeline for one file, because as we said before, remember, an audio file can be impacted by a million things, and if you only have one, it's not good enough. So in our example with this data set, these are the same people in the same setting, saying the same phrase again and again, just changing their pitch and tone and emotion. So it's kind of easy to detect what we want, and not in a vacuum in comparison with the others. I hope I'm making sense. All right. Yes. All right. So yeah, let's before I do the Fourier transformation, well, actually, let's do it now. So remember, we spoke about disentangling the waveform into its constituent frequencies, so all the frequencies together. So you can do this in Python, and it can be very helpful. So again, with Librosa, you do this short time Fourier transform, and it's a matter of one line. So again, you don't have to do any math, thankfully. It all happens automatically by some other very smart people that did it for us. So if I run this, I'm gonna get something like this. So again, for every frame of the sample rate of the resolution of the file, I'm getting a calculation of the frequency that is there. So on its own, this doesn't tell me much. So this NumPy array doesn't tell me much. This vector is not telling me much. If I plot it, however, and before I show you, I mean, I guess you have it all there, so I can run it as well. So I can do something called a spectrogram, and the spectrogram shows which frequency appears at which intensity across the time of this audio file. So this audio file is around 3 seconds, and most frequencies start somewhere here, and you can see that so you can think of every hertz point here on this scale as one frequency. So you can see that around this smaller scale of frequencies between this and this, which is what we said is speech, is the highest amount of frequencies here that constitute the waveform for this audio file that says what it says about the kids playing at the door. And there are some other very, very high frequencies that are there, like the vocal cords of the person produced them, and they were registered in the microphone and in the WAV file that we have. But our ears cannot hear them so much, or I mean, they don't make so much of a difference for speech itself. But they are here. So you can see here, you can think about every line here being one frequency, and we see how important it is by this hit scale here as time goes by. Beyond the simple spectrogram, which does this decomposition of the main waveform into the constituent frequencies, we can also do something called the MEL spectrogram. And a MEL spectrogram, which stands for melodic spectrogram, is again a visual representation of what we just did, but it shows how the energy of the different frequencies changes over time, but with these frequencies scale to match what we can hear. So basically, you can think about it as this is a better version, this plot is a better version of this plot, but only for the things that matter for our ears and make a difference when we hear an audio file. And it does so because we know we know as a fact that in the beginning, a change in frequency from 10 to 50 in our ears has double the impact as a change in frequency from 10,000 to 12,000. So in the lower frequency, the change is exponential to the end. So, but let's not dwell too much on this. the idea that this takes into account how hearing works and what registers in our ears, and takes that into account to produce the same plot, but focusing only on the frequencies that matter. So again, with Librosa and feature, we can extract a MEL spectrogram for the waveform, the sample rate that we have, and we're going to do it for twice as many frequencies as we do normally. And I can run this. It's very, very fast. And now I can also plot it once again. And here again we have frequencies. Again we have the frequencies across time, and the color here, the red color, means that it's more intense. These frequencies are more present here, louder and more present. But here now the plot has focused only on the part that matters for the human ear. So the rest is condensed. All the rest on the top and the bottom is condensed because it doesn't make difference in our ear. So we have the same spectrogram, but only for the things that matter. Finally, let's see what we can do with these metrics. I mean, okay, we calculated pitch, we calculated the root mean square, loudness, we calculated the MEL spectrogram, etc. But what can I do with this? So let's try to calculate the RMS and pitch, but for all the WAV files that we have here. So if we look at them, you have a collection of, I think they're about 60 or something. Len audio files. Yeah, we have 60 WAV files, and all of them are this very tiny kids are playing by the door thing. There was also another one, like dogs are playing in the porch. So they had two control ones, and you can see in the data set that the code here means the name of the actor, whether they talk about the dogs or the kids. The emotion is here. So 1, 2, 3, 4, 5 is the emotion. Then whether it's the second one or not, etc. So they have a code here that is explained here. So vocal channel, emotion, intensity, statement. So they have the emotion, but they can be like in a strong emotion. So 2 and angry. So 5 and 2 would be the angriest. So this is the angriest, I guess. Anyway, we can hear it, no? Let's quickly play it. Yeah, that's very funny. I know you didn't hear it, but I'm gonna play it once more now with you hearing it.
Kids are talking by the door.
Yeah, like super emotional about kids playing at the door, I guess. So right, let's calculate pitch for all of these files. Okay, so TQDM is here just to create a progress bar, but in the end I'm just running a for loop for every one of my files in audio files that I just created here. Like for every one of these files, I want you to calculate the same things. And what do I want it to do? I want it to load the audio. We are using Librosa load as before. I want it to calculate the RMS energy with Librosa feature RMS as we did before, and get the mean RMS. I want you to calculate the pitch. So again, within these two nodes that we specified earlier. So this is sort of a normalization per Aziz's question. So we are doing it here. We are removing any missing pitch values as we did before with NP is NA. And we are also getting the average pitch finally. So we get average RMS energy and average pitch for that audio file. And then we append the file name and the two values, and we put them in a data frame. So if I run this, It's gonna take about 3 minutes. Okay, that's a lot. And this TQDM here, all it does is this progress bar. So again, I don't know if you agree, but this is not like really complicated code. We're not going over it, but it's generally very, very simple code, line by line, in terms of what it does. While we're waiting for this, give me a few seconds to go grab a little water. Just a moment. I'll be back. While we're waiting, is there any question up to now about pitch, RMS? Okay, Merve, I feel like I should finish this part now, and then in the final 10 minutes, almost 10 minutes, we can do like a Q&A, and I can answer the question then, if that's okay. Yeah, no worries, no worries. Just so that we stick a little bit with these metrics, and then we'll come back to this question because it's very interesting. You're right. Well, it's a great question, though. Okay, almost there. 20 more seconds. I feel like we waited for code quite a bit today, for code to run, but almost there. It takes about 3 seconds per iteration, right? And again, this is 3 second to 4 second audio files. Imagine if you had larger ones, it would take a long time. So for 60 files, it took 3 minutes to calculate these values. But then the data frame looks something like this. So we have the file name, the mean root mean square value, and the mean F0 value. Again, on its own, it wouldn't tell us something, but in comparison to the other files that we have, now the RMS can tell us a lot. So now we can figure out which file is the, we can plot a histogram first of the two, and we can see that most of the files are a bit in the neutral sign in terms of energy, so they don't carry too much loudness. There are some exceptions here. Look at this, very, very loud. And also in terms of pitch, most of them are in the normal kind of side, but then there are some files with very high frequency relative to the others. Like the fundamental frequency is kind of high. So now with these in mind, we can calculate lowest and highest root mean square files. So we can ask Python to return to us the file with ID with a minimum value, right? So we figure out which one it is, and we can print it. So if I run this, I get this file having the lowest RMS score and this file having the highest RMS score. And I guess it's again, it's 0502, which remember is anger and the intense emotion. So let's hear this. Well, no, we can listen here. Sorry, I had the code ready. Oh my god. So I can try to play this sound again. So this is the one with the lowest RMS score, and it would sound like this.
Kids are talking by the door.
Kind of mellow and chill. And then if we take the one with the highest RMS score,
Kids are talking by the door.
yeah, I mean, we compared loudness here, so it's just simply the loudest of the files, but we could try to do the same for pitch, and then it would be something different. So maybe we can try. We can do it now. Let's do the lowest and highest pitch. Zooming F0. And then let's listen to these.
Kids are talking by the door.
Again, the mellow kind of thing, and then
Kids are talking by the door.
so this is the highest pitch one. So you can see that again with a little bit of creativity, I guess you can do many things in terms of figuring out which speech is what. Again, given the time constraints, we don't have time to do much more. But now you can, with the combination of speaker diarization and pitch calculation per frame, so per second basically of the video, you can also attach speech values. You could attach speech values to the SRT values. So imagine you have a data set where a speaker 0 speaks with this pitch and this RMS value. Then speaker 1 says this with this pitch and that RMS value. So in the end, you can see if one's increase in volume can increase the others. So you can do many things. So when a specific word is said, if that word causes a difference in pitch or loudness, so many things you can do here. I'm gonna stop here, and I think we have a few more minutes to answer some questions. So guys, feel free to answer questions. There is no bad question here. I know some of the things we brushed over maybe, but please let me know. As some people are thinking about questions, I think I'm gonna look at Merve's question here, which is very good. So basically, you're talking about these things that we use that are not really words, but they are part of our language, right? And so we have these verbal exclamations, as you say, like ah or t. In Greek, we have a lot of like we can also respond to someone negatively by saying yeah, and I think in Turkey you have something like that as well. Probably we got it from you. I'm gonna stop sharing for a moment now. So yeah, so basically what you're asking is they're not words proper, but they carry meaning and pitch. That's 100% true. So if they're not counted as word propers, how can they be accounted for by researchers, especially in more oral history-based interview transcriptions, where language may be more gestural and exclamatory? Again, a great point. So I know for a fact that in English, some transcription models carry these words, or like a majority of these words. I am sure at the same time that many of these words are probably not accounted for. So the truth is somewhere in between. I know that modern models capture some of these, and they carry them over to the transcript. But the fact that they are carried over in the transcript does not necessarily mean that they carry over the way they were used, or exactly understood how, or the model understands exactly how they were used. So you're pointing at two problems here: whether we have models that can capture these in transcriptions, and whether then another model that is analyzing text can figure out what they mean or how they were used at that point. And I feel like they are both equally problematic, but the second part is far more problematic. I think I've seen transcriptions that they can carry over their meaning. I would argue that if researchers are working with oral, are doing, interview, history-based interviews, I would argue that they have a bunch of interviews at hand, and they should be using transcription in the following way. They should be giving them the audio file to a transcription to do an initial transcription, and that they then listen and verify the transcription themselves. So I would not, in a research scenario where I have relatively few, albeit long, but few data points in terms of interviews and data that needs to be transcribed very, very well, I would not rely on an automated transcription. I would not rely on a model to do the transcription for me. I would use it as a helping tool to do the first transcription pass, and then I would validate on my own. And that goes far beyond capturing these verbal exclamations, as you say. I mean, it's generally good practice if you're working with high quality, like very qualitative work, where the transcript is actually all you have in terms of data, that this transcript is super high quality, and you can only get that if you validate yourself. And when I say validate, I mean basically do the transcription and correct the model throughout. Please, Merve, let me know if okay, cool. Then Aziz says, is there a way to programmatically find the complexity of the sentences uttered by a speaker? Yes, but this is a little bit beyond the scope of this class. That's more of an NLP task, a natural language processing task. So there are really cool studies right now about vocabulary complexity and grammatical errors that speakers do, and they programmatically check who speaks better language, basically, who's better at speaking the language. And it has been shown that in majority of Western parliaments, at least, the quality of the debate has fallen. Has fallen not sharply, but there's a steady fall in the quality of the language being produced in terms of vocabulary and complexity, which I hope is what you're saying. With audio, so we can do this, we can talk about this in a later point, but with regards to audio and what you could do with audio in terms of complexity, what I've seen happen is people work at seeing mispronunciations. So they use audio to figure out when something, and train models to be able to figure out when someone is mispronouncing a word. And in order to train the models, they use people that live in other countries and are learning the language. So they go to language schools and they gather data, and then they implement their algorithm. I think, no, I don't have the paper in the references. I can send it. Any other question? Okay. Sumaya, is there anything else? I mean, I'm done on my part. I don't think I have something else right now.
So thank you very much. I think there's no question from the audience too. Ben echo ediyorum. Let me check the chat. All right, so there's no more questions.
No, I don't think so.
Thank you very much, Yani. It was a wonderful session again. Hope to see you in summer school.
Yes.
And I would like to thank to the participants as well. So thank you very much.
Thank you, guys. I appreciate your participation and questions. Thank you, Sumaya, for the invitation once again.
You're welcome.